Sorry before I begin, because I did not have the microphone at dinner yesterday. So I just want to, first I should thank the organizing committee, which includes myself, for the opportunity to speak here. Some of you may be aware that I am actually replacing Askol Hovansky, who unfortunately was not able to be here today due to a heart surgery. He's doing okay, so we should all wish him well. But the reason I want to tell the story, I apologize, is because it's exactly 10 years ago that I first became a member of the topology community. It was the 2004 meeting at Oberwolfach where I first met Professor Masuda, and also I first met Taras. I think he's here. So it's a 10-year anniversary for me. It's an honor to speak. But it's the relationship between that 10 years ago and now is because 10 years ago I was still just a very recent PhD graduate, and it was actually not clear at all that I can be invited to this wonderful meeting at Oberwolfach, where Professor Masuda and Taras would be there. But at the very last minute, Raoul Bott had to have a surgery and canceled, and I was a replacement for Raoul Bott, which was and so all the conference participants were always teasing me the whole time, can you really fill the shoes of Raoul Bott? And now 10 years later I am here at another toric topology meeting, and now Askol Hovansky cannot be here and I am replacing him. So somehow every 10 years at a toric topology meeting I must replace a very illustrious mathematician. It's high pressure on my part. So today I will try. So my understanding is Professor Hovansky was planning to give a very broad overview talk on Newton-Okounkov bodies. So it is my attempt to fill his very big shoes and to try to say something which I hope Professor Hovansky would approve from Canada, where he's recovering from his surgery. So this is my attempt. So the first thing I should say is Newton-Okounkov bodies is a little bit long, so there is a abbreviation I often use, so it's just no bodies. So nobody is interested in nobodies. I hope that's not true. I hope it's the opposite. But I will often use this abbreviation. So my plan for the next 40 minutes is first, it's just really a very broad overview and an advertisement. And then I realize that Okounkov bodies have already been mentioned several times at this meeting. Valentina, for example, and Evgeny and Jesse Yang already mentioned in their talks about Okounkov bodies. But I think that for at least some of the members of this audience, Okounkov bodies is still relatively new, and maybe you are not so familiar with the historical motivation. So today I hope, again in the spirit of Askol Hovansky, to give you a little bit of the historical context. So to do that, at least the best way that I know how to do it is to go back to the very, very original theorem of Kushnirenko. So I will tell you about the Kushnirenko theorem. It's at least in my understanding, Q-Mars can tell me if I'm wrong, but for Askol it's really the foundational theorem that somehow grew and blossomed to what is now Newton-Okounkov body. So I will tell you about that. And then, again, hoping to fill the shoes of Askol, I will tell you at least my understanding of how Askol thought about this theorem and how it ought to be appropriately generalized. So I want to tell you about an old question of Hovansky, which was then later answered by Okounkov and then generalized by Q-Mars and Askol. And then if I have time, I would like to tell you a little bit about, Okunkhov's answer. Okay, and then if I have time, maybe a little bit about the recent applications and why it is exciting now in mathematics and relevant for this meeting, and perhaps a little bit of an introduction to Q-Mars' talk, which is right after mine. So. And I should say in advance, I am originally trained in symplectic geometry, and you see that in the title. At least so far, the talks which have mentioned Newton-Okounkov bodies, no bodies, have not emphasized so much the connection with symplectic geometry. And so, as a symplectic geometer, I'm very sad. So I would like to try to emphasize a little bit that aspect of the theory as well. And then the representation theory will be just implicit, somehow embedded in what I say. Okay? All right, so the very first advertisement, so I start with one. The very first thing to say, which has been said before, but I write it one more time, is that the theory of no bodies is it's a far-reaching, but anyway, it's a generalization of the theory of toric varieties in a specific sense, which I will say more about right now. Okay, so in general, a no-body, what is it? Well, what one gets out of a certain procedure is a closed convex body in some Euclidean space. Now, Bernd yesterday said that the interesting ones are the ones that are not polytopes. Unfortunately for me, I am generally interested in the ones that are, so apologies, Bernd. But anyway, as Bernd pointed out, they can be very interesting for Bernd and for me. But anyway, so there are closed convex bodies. So is a closed convex body in some Euclidean space, the dimension of which is determined by the dimension of the variety in question. Okay. And so I will say, so usually, well, no, not usually, I should say, often it's a rational polytope, and the examples such as were discussed by Valentina, for example, and Evgeny, the ones arising in connection with Schubert calculus, for example, and Bott-Samuelson varieties, they are actually rational polytopes, but in general not. So how can I say? Frequently in applications, they are actually rational polytopes. So that's good in the sense that it's familiar from the theory of toric varieties. And I should say how they arise. So of course it's associated to, so as the notation suggests, it's associated to some, say, projective variety X plus some additional data, as was also mentioned by Valentina. So there's a choice of evaluation and so on. So associated to a, say, projective variety plus some additional data. Okay, and in what sense is this a generalization? Well, one thing for sure is that if X is a toric variety, and this additional data that I'm hiding under the rug for the moment, the additional data is chosen appropriately so that it's equivariant and so on, then this convex body will be nothing else than the usual Newton polytope. So if n plus appropriate additional data that I'm hiding here, so if you choose the supplementary data appropriately, then you'll get the Newton polytope. Then delta x is nothing else than what we are accustomed to. Okay? Okay, so there's a familiar philosophy in this room, which almost I don't need to say, but I will say it, which is that we are all very familiar with the idea that if you have a geometric object X, which you want to study, and then you have a torus action on it, then the larger the dimension of the torus is in comparison to the dimension of the variety or the manifold that you want to study, somehow the easier it is. Right? Because, for example, if it's maximal dimension, if it's half the dimension, then we know we're in the situation, for example, of toric varieties or toric manifolds, in toric topology. And so somehow the dictionary is very, very good. Right? You can read off the geometric data that you want to read just from the combinatorial objects which you associate to it. But this is not perfect in the case when the dimension is too small. So for example, but nevertheless, there is some combinatorics. So again, many of us in this room are familiar with, for example, Goretzky-Kottwitz-McPherson theory. That's just as another example, where you may have a torus T acting on X, and the dimension of the torus is smaller than the dimension of X, but nevertheless you get some very beautiful combinatorial description via the graph cohomology of the equivariant cohomology of the space, and so on. But of course the GKM graph does not completely encode the equivariant geometry of the space. So we are familiar with this general philosophy. If I write here, is it impossible to see in the back? Probably yes. So as I say, in this room we are very familiar with this general philosophy, which of course is very vague, but the point is that if T acts on X, yeah, then, okay, so I leave it very vague, then somehow the larger the torus is in dimension, yeah, the more we can read, the more equivariant geometric data, I guess I should say. We can read off of some kind of combinatorics that we associate to this data, right? It's just a general philosophy, right? Okay. So of course, in the case of the torus variety, you just have the fan, and that's it. Okay, but in other examples like Goretzky-Kottwitz-McPherson, this might not be the case. So then the advertisement for the theory of no bodies is the following thing, that is the following, that this theory, okay, so this theory builds for you, yeah, combinatorial objects, well, namely closed convex bodies, which are often polytopes. Okay, builds combinatorial objects, yeah, of maximal dimension. Okay, so in the sense that it's the same dimension as, for example, a Newton polytope. It's half the real dimension of the manifold. So of maximal dimension. So as in, it's half the real dimension of your space in question. Okay. Okay, so so that's one part of the advertisement. The one part is that it's really maximal. That's one part of the thing I want to say. And the other thing I want to say is that it's even without any group action. You don't have to have a group action to begin with to build this thing. Now, of course, you have to pay a price. In mathematics, you don't get something out of nothing, so you have to pay a price. And of course, the price is what I'm hiding right now, in that you have to choose this additional data, which is a choice of a divisor, a choice of evaluation, and so on. And if you've been listening to some of us argue after some of the talks, you know that it's actually very important what data you choose. But anyway, so you do pay a price, but nevertheless, the thing that you get out is what I want to advertise as a great benefit. Okay, that you can build these things. So this is the work of Kave and Havansky, roughly Kumars 2008, 2009, something like that. 2009, something. And also independently by Lazarsfeld and Mustada for completely other motivating reasons. Lazarsfeld and Mustada were trying to study linear series. But anyway, they ended up doing the same thing, so roughly at the same time. So completely independently. But I should say, as I already implied, Kave and Hovansky's work was very much based on and motivated by a certain answer by Okounkov to a question of Hovansky. So this was based on Okounkov's work, I think, again, Q-Mars, you can correct me if I'm wrong, I think late 90s, I think. Yeah, so by the way, I should say that what I have written on the board already explains the name for this theory. So here's Okounkov, and here's Newton, okay? So that explains the name of Newton-Okounkov bodies. Okay, so that's my advertisement, and as I said, examples are the Newton-Okounkov bodies. The examples are Newton polytopes, pardon me. And as Valentina mentioned yesterday in her talk, Gelfand-Zetlin polytopes arise as examples, and even more generally, I think it was mentioned in Jesse's talk yesterday, this general string polytopes from geometric representation theory also arise as examples. So I have already mentioned something that fits in this category. So somehow there are many examples that arise. Okay, so that's my introductory advertisement. So now let's go to the Kushnirenko theorem. So again, for those of you who are not already familiar with what this story is about, let me go back to the absolute first motivating Kushnirenko theorem. Okay, so this is it's a theorem which is beautifully elementary to state, and I will give a sketch of the proof, just a sketch, but the sketch will hopefully illustrate that symplectic geometry, toric varieties, and algebraic geometry are intertwined in this story. Okay, so but the statement is beautifully elementary. So here we go. Okay, so let's let S be a finite subset of some integer lattice, and you are meant to think of these as exponents of a monomial. Okay, so if you have a list 2, 3, 2, 1, you are meant to think of that as specifying the monomial z1 to the 2, z2 to the, what did I just say? Well, whatever it was that I just said, you just think of them as exponents. Okay, so be a finite set of, and you're meant to think of them as multi-exponents. Okay? All right, now let's consider the system of n equations. And I apologize for a bit of notation here, but I can't avoid it, I think. Okay, so let's consider a system of n equations, okay, in n unknowns. So here we go. So the point is that this finite set of multi-exponents tells me exactly which monomials are allowed to arise in my polynomial equations. Okay, so I have, for example, let's see, so J. So the jth equation would be for some collection of coefficients in front of these exponents, and then z1 to the alpha 1, z2 to the alpha 2, etc., zn to the alpha n. Right? So again, just to remind you, you think of alpha as an integer vector, and then I have, and then I just think of them as the exponents for my variables, and then I decorate it with some coefficient, and I set it equal to 0, and I let j vary, so I have n of these such equations. Okay? Okay, so consider that. I haven't said the statement of the theorem yet. Where? So these coefficients, let me put them in C. Okay, and the variables are as I've just said, and then ask. Okay, solutions. So since these numbers may be negative, I didn't say that these have to be positive, so they might not be polynomial, they might actually be Laurent polynomials. So I ask for solutions in C star to the n. Okay, they must not vanish to ask for solutions in C star to the n. Okay, all right, very good. And then the statement of the theorem is as follows. That the number, so generically, which is to say for a generic choice of the coefficients, the number of solutions to this system of equations is given by computing the volume of a certain convex body. So that's the theorem. here we go. So the theorem, okay, so that was the setup, and the Krishna-Renko theorem says that for a general enough choice of coefficients, then the number of solutions to this system of equations star is equal, so let me give this a name, so let's see, n of s. Okay, so I'm taking generic enough coefficients, so the CJs don't actually come in. It's just you make some generic choice. It just depends on the s. Is nothing else than, okay, so there's some factor, but anyway, it's just the volume, the Euclidean volume of s hat, which is my notation for the convex hull of, you just take these multi-exponents, you think about them in Rn, right? Zn, you just let it sit inside Rn, you take the convex hull, it's a finite set, it's some convex polytope, and you just take the Euclidean volume. So it's the convex hull of S in Rn, which of course I'm thinking about as the thing that the lattice sits inside. Okay? So there are a couple of things that, again, if you're in this room, then you're supposed to immediately think, which is that there's a C star to the n torus here, right? So somehow toric varieties are somewhere lurking in the background. And the other thing, again, this is my symplectic geometry side coming in. So if you have a toric variety sitting somewhere, and then you see a convex hull, then you're supposed to think this is Atiyah, Gilliman, and Sternberg. You're looking at some moment map image, and you're taking the convex hull of some T fixed points. And so now I want to show you this a very, very brief sketch of the proof to illustrate exactly why those two things are really not just accidents, but they're somehow fundamental to the story. Okay, but before we do that, if you will allow me, actually, is that a good idea? Maybe it's not a good idea. Okay, never mind. I was going to do an example, but I'm already short on time, so forgive me, I will skip the example. Let's just go to the sketch of the proof. Okay, so sketch proof. Okay, so the point is to look at this problem both from a algebraic geometer point of view and a symplectic point of view. So the key insight, at least, well, this is my prejudice. I think there are probably many proofs of this, but it's my preferred proof, if you allow me. Okay, so the point is to think of C star to the n, yeah, as we like to, namely some open dense subset of some toric variety. It's the open dense orbit. Yeah, so as open dense orbit of some toric variety. Okay, and how do you do that? Well, this is very familiar, I think, to many of us. So you just take the usual embedding of C star to the n into projective space and then take the closure. So what do I mean? I mean, so if I have this finite list of multi-exponents, okay, as I had over there, then you take the embedding, so I'm going to just assume that everything is beautiful enough that everything I'm saying is true, like for example that this is an embedding and that when I take the closure it'll be smooth and so on. So let's just assume niceness things about S, but you consider the embedding, which is very familiar. C star to the n goes to, so Z goes to exactly the thing whose homogeneous coordinates are exactly given by these multi-exponents. So I apologize if the notation is confusing. I'm just swapping a little bit the notation here. So here, I apologize for this. I shouldn't have done it maybe. So here, the alpha 1 denotes the components of a given alpha. And I apologize here, I'm actually listing different multi-exponents, so I apologize for that notation. But the point is to put it inside a large projective space and then take the closure, as we often do. Okay. Okay. in that case, so when you have done that, then so then in that notation, this is just a 1 z to the alpha. Right? And then you see that if you have translated yourself into this projective space with this embedding, then this just becomes a collection of n linear equations over on the projective side. Right? Okay. Very good. So now I will just quote, I apologize, I'll just quote some symplectic geometry. The point is that there's a torus that's acting on this whole projective space, and you can think about XS as a Hamiltonian torus space, and with an associated moment map. And then just completely standard symplectic geometry and Hamiltonian actions on projective spaces tells you that the fixed points for that torus action on this axis, the image, is exactly given by the points, what are they called? I'm sorry, the points which are one on one coordinate and 0 else. Yeah, so these are the fixed points, and the images under the moment map are exactly given by these vectors. So therefore, by applying a Tia and Gilliman and Sternberg, when you take the moment map image, it's just the convex hull of the exponents, exactly that. So this really is the moment map image. Okay, so let me write that, because I just said it a little quickly. So let me write that. Oh dear. Okay. I hope you can still read. I'm sorry. Okay, it's okay? Okay, all right. So I just want to say, yeah, so so this is not meant to be scary. So from very, very standard graduate level, first course in symplectic geometry level, standard symplectic geometry, the moment map for the T action. So here I'm talking about the compact torus sitting inside of C star to the n, and then that transfers to a linear action on the projective space. So for the T action on XS has moment map image exactly equal to the convex hull. Well, okay, so a Tia, Gilliman, and Sternberg tell you, please remember, their famous theorem is that it is the convex hull of the moment map images of the T fixed points and that is nothing else than S hat. Okay? Okay, because it's just the convex hull of the exponents is what it is. Okay, all right, but now, again, putting on our symplectic geometry hat, please remember that it's also true that when you think about projective toric varieties from a symplectic point of view, you can, well, it doesn't have to be purely symplectic. I guess this is a more general story, which is that you can also interpret the lattice points inside of S hat in a geometric fashion, namely that the lattice points inside of this polytope are in one-to-one correspondence with a basis for the space of holomorphic sections over XS with the pullback line bundle from here, and the basis is exactly of T weight vectors for this torus action on that line bundle. And so it also has a representation theoretic interpretation, which is that, well, it's giving you exactly the decomposition of that T representation into irreducible representations. So that's something else to keep in mind. Okay, but let me just finish the sketch proof of the Kushnirenko, which is, on the other hand, right, what we're doing, well, what are we doing? We're trying to compute the number of solutions to a set of generic linear equations on a projective space. And now putting on your algebraic geometry hat, you know that's degree, that would be counted by degree. So here we go. Okay, So now putting on our algebraic geometry hat, okay? So sometimes we wear our applied math hat, and sometimes we wear a symplectic geometry hat, and now we're wearing our algebraic geometry hat. And we realize that for generic enough choices, in other words, for a generic enough choice of an appropriate codimension appropriate codimension plane inside of the projective space, we immediately see that n of s should be just the degree, yeah, of access inside this large projective space. Okay, but on the other hand, degree is a topological thing. We can compute it using the usual Fubini-Studi form on xs and just computing the integral of an appropriate power. So let's do that as well. So if you do that, then this is exactly n factorial of the volume, the symplectic volume of xs. Why is that? That's just because the symplectic volume of xs is defined pretty much by looking at the push forward measure for the symplectic structure on xs to the moment map image with the Lebesgue measure. So this is symplectic volume. Okay, but because it's a toric variety, the symplectic volume is nothing else than the volume of the moment map image. That's just because on a toric variety, the fibers have volume, symplectic volume 1. Okay, all right, so that was supposed to be my brief sketch of the proof, but again, I hope I have convinced you that toric varieties, algebraic geometry, and symplectic geometry, and in the background there's representation theory lurking because of this interpretation of these lattice points as t-weight vectors. Okay? So now, in the remaining 7 minutes, let me at least sketch for you Chovansky's vast generalization of this setup and Okounkov's answer to it. So if you are Askell Chovansky and you see this theorem, this is what you think. Okay, so Chovansky's question and Okounkov's answer. Okay, so as I say, this is a beautiful theorem which interlinks many things. So let's try to generalize. In particular, again, this is I think a theme of this workshop, which is that you somehow don't always want to just look at the torus. You also want to look at general reductive algebraic groups. So that's one thing that Askell also agrees. So let's let G now not necessarily be a torus. Let's just think about reductive algebraic. Okay, and let's imagine that we have a G representation not necessarily irreducible. Okay, so this is a G rep not necessarily irreducible, although of course we can take such an example. Okay, but anyway, we don't require it. And then let's imagine that we have a G invariant subvariety of the projectivization of V. So a G of variety sitting inside this representation. So suppose you're in this setup, okay? And so the examples that you should have in mind is, of course, so I apologize for ugly board work, but I'm running short on time. So the first example that, of course, you should have in mind is what we just discussed, right? T, the torus, is acting on the toric variety xs, which is sitting inside this projective space, which is a T representation. So the first example is, of course, Kushnirenko. This, what we just discussed. But as another very different, a generalization in a very different direction, yeah, you should also think of Bott-Borel-Weil. Okay, so the Bott-Borel-Weil situation is exactly also in this framework, yeah, where you think about some reductive algebraic group G, and then you do take an irreducible representation V, lambda, say, for lambda some dominant weight, and then you take and then x is the orbit of the highest weight vector, and then you're exactly in Borel-Weill. Okay, so this of course is different from Kushner-Renko, but it is related in this situation. Okay, so then in this context, it's well known that you can, so then the question is there something like Kushner-Renko hiding in this more general situation? Is there some polytope which takes account of somehow the representation theoretic and geometric interpretation, the data that is in a similar way to Kushner-Renko. And as a first step, and as a motivating first step, it's classical that you can associate a polytope to this. And again, Q-Mars can help me with the history here, but let me just say what the polytope is. Okay, so in this context, one can associate a polytope. So this is rather classical, or anyway older than the theory of nobodies. Okay, and it's this. You consider R the homogeneous coordinate ring. So X is sitting inside a PV, so it has one. Of course, you think about it in its usual graded pieces. And then because X is a G variety, certainly G acts on R. And of course preserves the graded pieces. Okay, so each one is some G representation. You can break it up into irreducibles. And so let's let MK, so I consider each graded piece separately, let's let MK lambda be the multiplicity with which a certain V lambda irreducible representation appears in RK. Okay, so the multiplicity of the appearance of V lambda in RK. Okay, then you can define the following polytope. And it's this, ready? Here we go. Delta of weight. WT for weight, it's because we're looking at the weights the highest weights of the representations that are appearing in RK. Okay, so this is the definition. And it's so you take the convex hull of the lambdas which do appear. So if MK lambda is non-zero, then you're going to think about that lambda. But as K grows, these lambdas also grow. So to keep things finite, I'm going to do a rescaling. Okay. And then, I'm sorry, convex hull of I messed up, I apologize. Take the union and then the convex hull and then a closure. Is that right, Q? Yes, okay, thank you. And now, again, putting on my symplectic geometry hat for just one moment, there's a theorem of Michel-Brion, which says that this is exactly the Kirwan polytope for the moment map of the maximal compact subgroup K sitting inside of the reductive algebraic G acting on X. So this is the Kirwan polytope. In particular, it's it's a polytope which has a symplectic realization. Okay, thank you very much. Of K acting on X. Okay, all right, so let me just say the question and briefly the answer. I apologize for going over time. So here's the question of Hovansky, which is there, I'm sorry, so this polytope is too small in dimension. It's very small in comparison, right? It's the rank of G. And X may be much larger in dimension. And also, it only encodes whether or not the representation appears. It does not say anything about the multiplicity with which it appears. And of course, it says absolutely nothing about actually providing a correspondence with a basis of V lambda. So the question of Askold is there a larger polytope which accounts for everything? Yeah? Which accounts for the multiplicities and the individual a basis for the individual v lambdas. Yeah, so that the lattice points inside of it would actually give a one-to-one correspondence between a basis for the whole representation. Okay? Okay, so so I am completely out of time, so let me just say that the answer of Okounkov, which motivated Kumars and Askold, is to give a yes to this. So Okounkov told Askold that he can do this. Okay? And then based on Okounkov's answer, Kumars and Askold actually managed to do both of them. Okay? So this is Kave and Havansky. So that is my brief historical motivation for what Kumars will tell you more about in a few minutes. Thank you very much for your patience.